So in this video, we're going to take a look at example 2.2, and this is similar to analysis, I think it's problems 1 through 6, where you're looking at some data out of testing that gives you load and length for the elastic region, and then I believe it is stress and area, or load and area for the plastic area, for the plastic region, excuse me. And then you are calculating the stress and the strain, and you're doing that for the elastic in the plastic region. And if I remember correctly, true stress and strain was not particularly emphasized in that problem. And so you're asked to use the data provided to fill in some of the pieces of information. So you're given an initial diameter. And so let's take a look here. You're given some initial information. You're given, is that going to focus? It is. Okay. You're given the diameter, and you're given a table that has the loading and the length, and that's for the elastic region. And so in order to get the stress, right, and so we're looking at stress, it's simply the loading over the area in the elastic region, right? And so we can use our initial area and our initial diameter to get this for the elastic region. Now, in the plastic region, we'll have some stress level that's equal to the measured applied loading and the change in the area due to plastic deformation. And so we have two different ways of calculating stress there, one that acknowledges a change in area. And so we recall, right, that the area of a circle is just pi d squared over 4, right? And so that's something we should always keep in mind. I'm going to box that so it's clear I'm not dividing that all by d0. And so what else? So we know how to take the loading, right? So P is our load, L is our length, okay? And so this is the kind of information that we know. We know that our strain, is a function of my change in length over my initial length, right? So if I have a measured length that has increased from my initial length, I will have a positive strain. And so as I am putting a tensile axial load on this object, right, keeping in mind that we have a rod and we're putting an axial load that is also tensile on this thing, it's going to stretch. L is going to get bigger, which means A is going to get smaller and smaller until it necks. And then we've got some failure analysis going on. So then after I've kind of done my initial data filling, if you will, to get a table of information, then I can make a chart. I can graph how my linear portion looks, right? And then I can extrapolate what the slope of that looks like. What can you do here? You can take out a piece of paper and a ruler and graph it. If that's not something that you are interested in doing, you can throw it in Excel. Should be a pretty quick exercise to toss this thing in Excel and approximate the modulus of elasticity from that. And then if I zoom in example 2.2 to show you this, right? So you have a line that has a slope of E. And then if I go from my engineering strain, or just my strain here of 0.2%, so that's my yield strength, I draw a parallel line and intersect it to my curve. And so as I look at the point of intersection between my 0.2% line and my 0 line, that also deals with some plastic deformation here. We've gotten away from linear. Now I get my yield strength in whatever units my y-axis is in. And as I'm looking at my graphs, I can usually glean this information pretty simply on paper as long as I'm careful with my graphing, or I can throw it into Excel and then approximate it on the screen. Get creative, use Paint, take a screenshot and throw some lines on there. However you need to modify this to approximate these values off the chart. I'm hoping that adds some clarity to your first multi-part problem, and example 2.2 is a good place to look for more guidance here. And so you can take another look at example 2.2 if you'd like, and please post questions in the discussion board. I think that would be helpful for everyone. Oh, the last piece I did want to highlight is this reduction in area concept. So if you didn't catch this out of the text earlier, your reduction in area is a measure of how much the area changes based on its initial area and the loading, right? So this is data. We know what the initial area was, and then we know what the final area is using the data provided in the problem, so we can get a sense of what the reduction in area is. And I think that was the last thing for this example. Questions always welcome.